quite like one question here. I mean, if you do not have independent data, what do you have to watch out for doing national output? And the answer is, the answer is there's no general rule, but it all depends on what kind of dependency structure you have on your data. So do you have Markov data? Do you have, are they martingales? Are they whatnot? So there's no general receipt when you have independent data. Okay. One last example. XN is IID uniform on theta plus 1. Okay, so then the likelihood function is the product. I mean, so this means the density of a uniform over AB is B minus A, so this thing has density 1. So theta this thing, which is the same as the indicator of the max xi minus 1 theta min. Yes. So I mean this function is either the likely function is either 0 or 1, so it's maximized for a value of theta that is bigger than the max minus 1 and less than the min of the observations. So the maximum likely solution exists, but so exist, but any theta in that interval is a solution, so it exists, not unique. So as you probably understood, the uniform distribution is the first place to go for counterexamples. Yeah. Okay, so then we'll say invariance of families. So what this means is if you have an ML, which is the maximizer of the likelihood function, okay, and you now want to estimate another estimate, so you want to estimate some function of the data, which you use these functions have or data. Okay. Then ml is tau evaluated in ml. That's nice. And we used that already in some of the exercises where we just plugged in the mean in the probability function exponential. Okay, so this is 0, 7, 10, and 8. Right. So proof. So t is a function from vertical phase to, let's say, lambda, which is going to be the range of tau. Okay, so tau is a function. Okay, well, since tau is a function of this analysis method, this is an element in lambda. Okay, it's a function, so it's only one element in lambda. So let's call, or where we're headed, let's call that element lambda hat. Lambda hat. Okay? So that is a unique element. So for each lambda range of tau, we define these to be all thetas, such that tau equals lambda. Okay, now define function m over lambda to be the supremum or restrict from perspective to be this theta lambda of L theta. So this is what's called the induced Lipper function of the second loop. Okay. Well, sort of by definition, this thing equals now m lambda is our definition. Okay, this is smaller than this pyramid. Space. Okay, but the definition of the maximum likelihood estimator is the value that contains this. Okay, so this is equal to this. And this is true for any so then there we have it.
Can you say something about this induced, what's the point to have the expression or something?
Of the induced likelihood function?
What's the point with it? Or
Well,
why do we have it?
The point of it is that it's no point making it if tau is a one-to-one function. This is true even though tau is not one-to-one.
Exactly.
So then you sort of need to make the label sets. So then it's just something you use to prove this fact. Okay. So it's nothing that pops up. I mean, the only time we'll see this function is in this proof. I think.
Yeah.
I haven't seen it elsewhere. So but I mean, you might see similar constructions if you want to maximize some likelihood function over a restricted area of the parameter space. That's okay. I mean, then you define another likelihood function, but anyway, okay. So it's in this book. You'll see it. And we had not. It hadn't been necessary to make that function if we had assumed that tau is one-to-one. But we don't want tau to be one-to-one as this holds even though tau is not one-to-one. So that is actually the content of this example. So. If these are independent Bernoulli P, then the log likelihood. So the log likelihood function. Differentiate, etc. You will see that the maximum likelihood estimator is the mean. Okay. Now, a typical thing in this case is to estimate the variance. So the variance of an x is P1 minus P. This is the variance of x. Okay. One reason why you might want to estimate this is, as you know, or as you should know, this thing tends in distribution to this. Okay. You'll agree? Now, let's say you want to make a confidence interval. We haven't done confidence interval, we've probably done other courses. Let's say we want to make a confidence interval for P. Then, this plus minus 196, 0.5 confidence interval times standard deviation of decimeter, but you need to estimate this thing. Okay? So, in order to estimate this thing, you need to estimate, mistaken, this is, but it's not an equality here. Okay, so this is what I call, No, I messed up the notation completely, but you get my point. You know, so I mean, this thing pops up as a standard deviation of your estimator when you want to make a standard interval. Okay, it's a standard confidence interval. Okay, this function here is like this, with the maximum one for something. But point, you know, so this is not the one-to-one function. So the natural question is, okay, so how do I estimate this thing? Okay, and there is, okay, one estimator of this thing is the maximum likelihood estimator. Okay, I'll use the maximum likelihood estimator. So by the previous theorem, we now know that the maximum likelihood estimator is this. So in order for the theorem to hold for these type of cases, we have to make that induced likelihood function. Questions? We're quiet today. We're always quiet. It's extremely quiet. Okay, so well, I mean, when we're at it, talking about the likelihood, I think I'll say some more about likelihood. So just to recall, we have in the background here. From now on, it will be silent still that we have independent data from some density. So I don't, we have that in the background, okay? So I don't have to write that down all the time. Okay. Yes. I've alluded to the score function several times, but now and I will also not mention all the differential where I assume, I mean, that it being differentiable, etc. I will take that for granted for a while, but you know, so you'll understand what you need to check. It's actually true for all these definitions to make sense. So the score function, which I'll denote as small, which is probably a bad choice because it looks like an N, but it's a U. Is the derivative of this thing, which is the sum first this is it's a score function. Okay, so I already regret my notation. So can I change it? way more in line with what I had in mind. What I wanted to define this small thing for one data point. Okay, so this is really important. So I wanted to not this and not this. Oh, sorry. Okay. So just for one x, so to say. Okay. Is that clear? So basically just saying that. So this value in one point x is the derivative of log. Which is equal to that. Okay. That's what I have in my notes. So I don't mess up. I think I'll stick to that definition. Is that clear? I'm sorry about. Okay, so then we already know that ML, provided it exists, is the solution to okay, or if you want, I'll write 0. You also, what can you say about the score function as around the expectation of the score function? This is, we had this as an exercise and I mentioned it a few times, but this is 0. Okay? You remember this thing, right? Which is important because, so if you've done this exercise, you'll see that when it comes to consistency, so I mean, our maximum likelihood oscillator is a solution to this thing. Let's say this. Then it's mean. Okay. So our maximum likelihood estimator solves this thing. This thing viewed as a random variable this is a mean of independent random variables. No? So it converges. Provided this thing has finite expectation, the law of large numbers ensures that this conversion probability to the expectation of this. Another way? We sort of should expect that a 0 of this thing the maximum likelihood estimator solves this thing. So we should expect that the zero of this thing converges. Like this should sort of tell us that this ought to converge towards a zero of this function. Okay? A zero of this function, which we'll see, is this expectation when both things are evaluated in true value. Because then this thing is zero. It's what we've done as homework. Okay? Now suppose that the model is misspecified. Yeah? Then this thing converges in probability to the expectation of that. But this is just a function that we wrote up. We came up with this function. Yeah? So then, if the data is really, it's not normal, but gamma or something we don't know, like some independent from some density g, then this expectation is taken with respect to that density. And then expectation with respect to that density and the derivative of this thing. I mean, so this is just a consequence of what we said. The data are, and then we assume that our model is correct. But if our model is not correct, then this thing is not zero, which is easy to see because you used in the proof. I mean, in the proof of this thing being zero, we use that you take the expectation with respect to the same density as we said were the density of the data. So this is not zero, which means that this thing will converge to something else. I mean, it will not converge to it will not converge to the true value of this distribution. Now, the true value of this distribution doesn't really make sense because it's a wrong distribution, but you get my point. So, I mean, these things are more subtle than... yeah. We'll get back to it. Okay. We'll also define the Fisher information matrix, also called expected information matrix. I'll denote as J theta, which is then the variance theta U theta x, which is the variance of the score, and the minus. This is also these qualities here have also been part of the homework, and if you haven't done it, you can look at my solutions that go out soon. Okay, so this is then a P times P matrix, which is so it's basically the Hessian of partial derivatives. Okay, so if let's now assume that P is 2 to make this clear, then this is the expectation. This M1 squared log equals 2, and then we'll also define Jn theta. So now it's very important to notice where I use subscript n and no subscript n. Okay, so notice that with the IID data, this thing does not depend on n. It's just the variance of the first derivative of the density. Yeah. So we will also have minus 1 over n. Okay, so we can solve I'm sorry for the measures, but the observed information. With IID data, this is negative empirical mean of independent IID random variables. I mean, so these are independent IID random variables. But so when, as I told you, when you see a mean, there are independent things. So assuming the expectation of this thing is finite. This thing converts in probability to, under some conditions, this, and clearly J naught equals the expectation of J, and there's no hot, I'm sorry. Okay, so Fisher, observe, and Fisher. So notice now this, we were supposed to talk about methods of finding estimators, but when we first start talking about maximal likelihood estimators, I think it's too bad if you don't also talk something about the properties of maximum likelihood estimation. And the things I go through now will be covered in much more detail in the course on large number theory next semester, but if you don't take that course, you should know about these things, and it doesn't hurt with a light introduction if you're taking the course. Okay, so consistency of MLE. So, as a denote true value of theta by theta naught. Okay. Which means that I want to say that the data are IID from a density theta naught. So, and we'll be working on the assumption here that we have correctly specified our model, so to say. Okay. So is the ML estimator consistent for theta naught? That is, do we have consistent is just another way of saying probability to theta naught. Now I will do myself, but fix some theta and theta, then n and theta, which is then the mean log f Just notice one thing now, which is also silently, tacitly understood, is that now we're looking at regarding the likelihood function, even though I haven't changed notation, so it's a blatant abuse notation. I haven't changed notation, but I look at regard the likelihood function as a random variable. Okay. When we start out, we say okay for fixed x. Now suddenly random variables, but Okay, so for any fixed theta, assuming, so this is a sum over independent variables, assuming this thing has finite interpretation, which is reasonable, then this, whether weak low large numbers converges to log Okay, so now, so what's the right index here? Because now you have to be careful. Because now I said just fix on theta, yeah? And this is theta not. Because of course, these are, I mean, we said that we sample data from density, theta naught. So if you just plug in some theta, and this thing converges to the expectation taken with respect to true density. That's what it converges to. Okay. So this might be confusing, but let's call this thing. Let's define this function just L, no index n. Theta. So now we can look at this. Now we can regard this limit as a function of theta. Okay. And then to write out what's L theta. And even though I here assume that the distributions are absolutely continuous, I mean all this carries over to the discrete case, so it's just notation to thing. Okay. Well, so you know, I said maximum likeliness method maximizes this thing. This thing converts in probability to that thing, so it seems reasonable that the maximizer of this thing, our ML estimator, should converge in probability to the maximizer of that thing. You agree? Right. Okay. Under certain conditions, it is true, but it should also make intuitive sense. Now, maximizer of n theta not log fx theta is the minimizer of a certain function call L f theta not f theta. Now I change the location of these thetas, where the KL by So we could have written this function when we're working inside one parametric family. I could have written like this, or maybe that would be sufficient to understanding that we're inside this parametric family. Okay. By parametric family, I mean so all that's so the same. I think of the normal distribution with parameters ranging over parameter space. The reason why I wrote it like this is that these definitions are the same. If you just have two different densities, even though they do not belong to the same distribution. So I mean that can be a gamma, that can be a normal. Okay, I mean that hence the notation. Okay, so what we define here is what's called the pullback Leibler distance, or it's called the pullback Leibler divergence, or we call many other things. I know it's also called relative entropy. Point is that the Kullback Leibler distance measures the distance. The way we should think about it in statistical terms is that it gives some distance which does not mean that it's a metric thing. So you give some distance between, I mean, how far is this model from that model? Okay, so yeah. Okay, so we'll take a break to quarter fast. I think I'll continue maximum output stuff. Maybe do one exercise.